Hello everyone and welcome to another Nanotalk. This Nanotalk is a recording of a Lightning user webinar with Dr. Trevor Almeida, who uses in-situ biasing and heating simultaneously to investigate the magnetostructural transition and current-induced domain wall motion in iron-rhodium thin films. Now we will switch to the recording. The presentation starts after a short introduction of the speaker, and after the presentation you can also listen to the Q&A with the audience. So I hope you enjoy this Nanotalk.
But of course, especially a warm welcome to our guest today, Dr. Trevor Almeida from the University of Glasgow, and I would like to take a minute to introduce him to you. Trevor is a research fellow in the School of Physics and Astronomy at the University of Glasgow. He obtained a Master's of Engineering and a PhD in Material Science at the University of Nottingham, where he then held a one-year fellowship focusing on the transmission electron microscopy of metal oxide nanoparticles. Trevor spent 4 years as a postdoc in the Department of Earth Science and Engineering at the Imperial College of London. This position included a one-year research visit to world-renowned electron microscopy institutes like the Center for Electron Nanoscopy in Denmark and the Ernst Rüsker Center in Jülich, Germany, where he combined in-situ TEM experiments with electron holography to visualize changes in magnetization in magnetic minerals. Trevor then decided to expand his research further to include visualizing magnetism of complex nanostructures for technological applications using the world-leading TEM for a range of Lorentz microscopy techniques at the University of Glasgow. His current research is focused on combining in-situ TEM with magnetic imaging to visualize directly dynamic magnetic processes in thin films and biomagnetic nanostructures. So that was my introduction to you. So I hope you enjoy the presentation of Trevor. I will be now handing over the screen to Trevor. And he's already there on the camera. Hi, Trevor.
Morning. Hi.
Morning.
Thanks very much, Olaf, for the introduction, and good evening, everybody, or afternoon, or good morning, depending where you are. My name is Trevor Almeida from the University of Glasgow, and my presentation today is focusing on a very interesting system called iron-rhodium, where I'm going to use a series of in-situ techniques with complementary series of Lorentz microscopy techniques to study the magnetostructural transition in this very exciting system of iron-rhodium. And this was a joint project with colleagues at the University of Leeds who synthesized the samples, but all the microscopy that you're going to see is performed at the University of Glasgow. So as we know, if we're trying to improve the functionality of devices, or essentially make them more efficient, or try and make them smaller, or cram more space, say in data storage, into smaller devices, we constantly need to try and improve the material properties. And to do this, we really need to examine the functional properties of these magnetic materials on their localized scale. And so this is true for magnetic data storage, where we can think of racetrack memory, or domain wall movement, or there's been a lot of interest in skyrmions, and using current to try and move skyrmions as well. But this is also applicable for nanomedicine, whether we look at MRI contrast agents, or hypothermia treatment of cancer using magnetic nanoparticles, or even combining cryo-EM, so we look at the uptake of magnetic particles within cells. And also something that I've done quite a bit of, Olaf mentioned, is looking at very small magnetic grains of magnetic minerals and see how they can change as a function of temperature as well as chemical alteration. So there's a wide range of applications trying to combine in-situ TEM with magnetic imaging. So as I mentioned, the material that I'm going to show you today is a very exciting material. It's called iron-rhodium, and the phase that we're looking at is very much equiatomic, so pretty much equal proportions of iron and rhodium. And it forms this very nice cubic CSCl structure. But what's interesting is that at room temperature, we have magnetic moments from the iron atoms, but they lie anti-parallel on certain planes. So the net moment is actually cancelled out. So at room temperature, it's a very nice antiferromagnetic material. However, if we heat the material up, say to 100 degrees centigrade, what we do is we induce a magnetic moment from the rhodium atom, and we also induce the alignment of all the iron atoms in one particular direction. So it goes from being a very nice antiferromagnetic to actually quite strong ferromagnetic material. So we can sort of show this phase that we've got of ectoatomic iron rhodium just at the bottom here with its antiferromagnetic phase. And then as we heat it up, it forms this ferromagnetic phase. And then as we heat it up further, it forms a paramagnetic phase above the Curie temperature. And this is very important to something I'm going to show later about the sample preparation and how this is affecting the phase. But we can also just look at the magnetization as a function of temperature. So at room temperature or below room temperature, it's antiferromagnetic, as I mentioned. As we heat it up, we can actually see it becomes a very strong ferromagnetic material. And then as we keep on heating, it becomes paramagnetic above the Curie temperature, as we'd expect. But something associated with the change in its magnetic properties is the change in the actual volume of the unit cell. So it goes from being antiferromagnetic to ferromagnetic with the associated 1% increase in its actual crystal volume, which is important to note, and I'll talk about more later. And one thing that we really want to look at in terms of actual practical applications of this material is trying to use it in devices. So if we think of this transition, it's actually quite nice because it's close to room temperature, so you don't need to really cool like a lot of other materials. And what we notice is in its antiferromagnetic phase, it has a resistance. And then as it goes through the transition, because it becomes ferromagnetic, its resistance drops quite heavily. So if we can control this position of the essentially this transition, we can use this in a device by looking at changes in resistance as a memristor device. So essentially looking at bits 1 or 0, depending on what the resistance is. So there's quite a very much interesting material for looking at memristor devices. So just to talk a little bit about the samples themselves, these were grown at the University of Leeds using DC magnetron sputter co-deposition. We used a series of iron rhodium targets, and they were deposited directly onto MgO or gallium arsenide substrates. And I'm going to show you 3 samples today: iron rhodium on NgO, iron rhodium on a nickel aluminium buffer layer, which we thought about using as a contact layer, and planar iron rhodium, where essentially the substrate's been etched away by hydrofluoric acid. So all we're left with is a planar thin film of iron rhodium. We can then transfer these samples, depending on which ones, onto TEM chips using either a gallium FeRh, which we did in the beginning, and then during the project we actually we were fortunate to get funding for a plasma xenon FeRh, which we used in the later part of the project to both form cross-sectional and planar iron rhodium samples. And this was important because essentially we wanted to transfer these samples onto either wildfire heating chips, which are then used in the lightning holder, or lightning chips, so we can apply biases across this line, essentially, so we can put current pulses through the sample, which I'll show a bit later. Okay, so one important thing to talk about is essentially trying to create samples on these chips. So I would hope that maybe many of you are familiar with making cross sections of thin films. But one thing we wanted to do is really try and get a planar thin film. But to do so, we really need to get rid of the substrate. So here we can see a protective platinum layer. We've got the iron rhodium thin film at the front and the MgO. So we want to mill away the MgO substrate, so we turn it round and essentially mill it from the back side using decreasing ion beam currents until it's essentially about 1 micron thick. And then we can undercut it, attach it to the easy lift. And in the first instance, using the gallium FeRh, the geometry didn't quite work out to be able to place it on the chip as well as have the gas injection needle in at the same time. So to get around this, I deposited some platinum on the edge, which I'll explain in a couple of slides. To place it on the chips, we used a 45-degree holder, which was previously designed by DENSsolutions. And this allowed us to good geometry, essentially, to put it both on the chip, but then also use the ion column to anneal it from the front side so that we can get a nice planar thin film of iron rhodium. So as I mentioned, we didn't have the gas injection system available when we placed it down, so we pre-deposited a platinum ridge and then used the electron beam to essentially raster it across the interface between the platinum deposited on the side to essentially weld it in the first instance, and then we can essentially take the needle out, tilt it, and add additional platinum welds on the edge to really sort of secure it down. Then we can essentially mill it from the front, all the while not exposing the iron rhodium thin film to the iron beam because we don't want to damage it until it's electron transparent. And here's an example of it being electron transparent with some very nice magnetic domain walls formed by Fresnel contrast. Okay, so that was about sample preparation of the planar samples. And then all the characterization was done using our gel ARM 200 cold FeRh, otherwise known as mag-TEM. So it's got all the usual sort of features of gel ARM. It's probe corrected with a series of voltages, although all the experiments I did was at 200 kV. It's got a high resolution stem, chemical mapping using EDX or EELS. But the main reason and why I use it and why it's called the mag-TEM is because it's got a Lorentz lens, so we can turn the objective lens off, and so the samples sit under magnetic free conditions. And we can use a series of segmented and pixelated detectors to try and image the magnetization from the sample. So this is just a first overview experiment of, this is the iron rhodium that's had the substrate etch. So everything in this field of view is a planar piece of the iron rhodium where we've got two bend contours in the middle. And on the right-hand side, we've got a small angle electron scattering view. So this is in diffraction, the central spot, and any structural information is well outside the field of view. So any deflection from the central spot is actually due to the change in the magnetic state. So in these videos, I'm going to show how we heat it up for 20 degrees, up to 140 degrees, and then back down to 20 degrees. So what we'll see is, as we heat up, we see nucleation and rapid growth of domains until it becomes in the fully ferromagnetic state. And you can see all the intensity in the electron diffractions actually form this sort of arc. So all the electrons are being deflected away from the central axis by these large domains. And then as we cool down, we can actually see these domains start to disintegrate and some of the contrast going back to the central spot. And we can see variation in the bend contours because there's localized strain due to the phase transition and the volume change. So this, like I said, this large field of view, there's a lot going on there. And to better understand the dynamics of the transition, we really want to sort of look at this in much higher resolution. So to do this, we use the technique that Glasgow is quite well known for, differential phase contrast imaging, where much like normal STEM, you scan the probe across the sample. In this case, it's under magnetic free conditions. And if the sample is of uniform thickness, the probe will be deflected by different directions of magnetization and domain walls. And this is essentially by the Lorentz force of the magnetic properties of the sample. So if we think of the beam being deflected by the magnetic domains, then they would have variations on this 8-segmented detector, where the beam would be deflected across the center, and we have variations in intensities across the different segments of the detector. And then we can use these variations, or essentially the difference in the intensities, to try and recreate images of the magnetic induction. So here we can see a planar view of the iron rhodium as a function of temperature. At 60 degrees, it looks fairly noisy and pretty plain. As we heat it up, we can see sort of nucleation at small vortex states. And then as we continue heating up into 100 degrees, we can see formation of very large domains of quite large areas, and we can say that this is in a fully ferromagnetic state. Then if we cool down again, down at 80 degrees, you can see it's still pretty much in a fully ferromagnetic state with large domains. So there's hysteresis on cooling versus heating. At 70 degrees, we can see these domains start to disintegrate. And then at 60 degrees, we can see we have some residual vortex states. So again, this sort of signifies hysteresis of cooling versus heating. So what we want to do is we want to try and clean up these images because they're not particularly clear, they're quite noisy, and you get variations in intensity. And so if we have an example of what the probe of the scan beam might look like in a polycrystalline film, we can see that it's not exactly flat. We've got variations or non-uniformity of the intensity within the probe. And so this is from an example of a permalloy, which is polycrystalline. So we've got lots of little grains. So we'd have effects of diffraction contrast, deflecting the beam away from the optic axis. And what we're trying to see here is we've actually got a domain wall present here, but it's not very clear because of all the polycrystallinity. So to try and clean this up, we can use a pixelated detector, where essentially we have 256 by 256 detector, and at each scan pixel, you can take an image of the beam. And essentially what we can do is apply a mask to the beam. So rather than using the intensity across the whole probe, we can just measure the movement of the edge. And you can see quite a stark contrast in change of the noise and the signal. And this domain wall is very much clearer after we apply this mask and essentially perform phase correlation of the scan beam. So that's one way to sort of use pixelated DPC rather than conventional segmented DPC. And here's an example of the etched iron rhodium at 80 degrees. And in this case, we can see that it's got phase coexistence where we apply a threshold to the deflection of the central spot. So the darker regions here are antiferromagnetic, and these nice, bright, colorful regions are ferromagnetic regions. And we can see the presence of quite complex domain structures. So we've got sort of an amalgamation of vortex structures in large domains, but we can also identify quite small vortex structures down to just under 100 nanometers. So this gives us a nice indication of a sort of mid-transition state. So then we can try and follow this transition as a function of temperature, looking at the same sample. So here we've got the sample at 70 degrees. We can see a sort of complex domain state with a few vortices around it and sort of spuriously through the sample. As we increase temperature, we can see the nucleation and growth of the central spot or complex domain, as well as nucleation of new magnetic states. And this will happen until we keep on increasing temperature. And we can also see the formation of sort of uniformly magnetized strings across the sample that join these different states as well. And if we keep on heating, essentially we can see that with these magnetic vortices and strings tend to agglomerate from their sort of small localized domain size into quite large domain states as we go into the fully ferromagnetic state. So this charts a sort of dynamic progression of the dynamics of the domains as a function of temperature. So then we can also cool down. So not much happens when we cool down to 80 degrees, down to 72.5, not too much changes. And then as we start cooling further down to 70 and 65, we can see the short range, well, breaking up of the long range domains until we get these sort of breaking up into smaller string-like uniformly magnetized domains that sort of link the domains together. And if we keep on cooling, we can see we've got another complex domain state that happened in the first instance when we started heating. And it's thought that these sort of domains tend to nucleate and disintegrate in the same place, probably due to structural defects in the sample. It's worth mentioning that this has obviously been scanned over the same region many times. So we also do get sort of buildup of contamination, which you can see this sort of band on the right-hand side there. Okay, so that was looking at the dynamics in a planar sample. So now I'm going to move on to the cross-sectional sample. And here we have cross-sectional iron rhodium on the MgO substrate. So we can see the MgO substrate there. The iron rhodium is grown epitaxially on the substrate. It's around 50 nanometers thick. And then we've got the protective platinum from the fib on top. We can perform chemical analysis. Here, this is just some EELS spectrum images showing the iron, rhodium, and oxygen from the MgO substrate. We perform a high resolution imaging. And here we can actually see the crystal structure quite nicely, where using the Z contrast, we can see the much heavier rhodium atoms are quite bright, interdispersed with the lighter iron atoms with a lower contrast. We can also look at the interface, and here we've got the MgO and the iron rhodium, and you can see it's actually quite nicely epitaxially grown across the interface, although there are slight variations in the lattice parameters between these two phases, and so you will find some variations along this interface due to strain. Okay, so that's looking at the chemistry and structure of the sample. So now we want to move on to the magnetism of it. And this is essentially using pixelated DPC. So we've got our polycrystalline platinum layer at the top, which is protective. we've got our iron rhodium layer in the middle, where we have some sort of structural defects which form contrast in the middle, and we've got some MgO substrate at the bottom. And what we're looking here as the interfaces is this large green band, and this is due to the change in mean potential between the platinum protective layer and the iron rhodium. And we also see a large red band, which is the change in mean potential between the MgO and the iron rhodium. But what's not so noticeable is we've actually got this very thin green band at the interface between the iron rhodium and MgO. And what we know is that because there is a slight difference in lattice parameter, there is a little bit of strain between the MgO and iron rhodium. And if you remember to one of the first slides I showed, that there is a volume change within the transition. So it's thought that this localized strain just at the interface actually induces a small ferromagnetic layer just at the iron rhodium surface. And this is very much backed up by bulk measurements in the literature. It's quite interesting to see. Okay, so that's looking at room temperature or low temperature. So now I'm going to show a couple of videos of essentially heating up the iron rhodium through the transition. So on the top, we've got our platinum layer, in the middle is the iron rhodium, and at the bottom is the MgO. So if we play the movie, what we can see is we actually get nucleation of these two little domains at the bottom. They kind of look like little crocodile eyes peeking their head above water. Then as we keep on heating, what we'll see is that the domain actually grows across the thin film, becoming quite dark, and also further into the top of the film throughout the transition. So this is quite nice. We can actually see in cross-section the formation of these ferromagnetic domains. So this is the same sample, but in this case, I'm just going to cool it down. It's worth mentioning that this is actually very bright in the iron rhodium. It's purely because in this case, the sample was magnetized in the opposite direction rather than the dark direction in the previous example. So as we heat the sample, we can actually see it becomes darker at the edges because it's becoming antiferromagnetic. And as it sort of cools further and further, what we'll see is a nucleation of a little vortex structure just in the middle. And then it becomes fully antiferromagnetic as we cool down beyond transition temperature. So we can get a better idea of what's going on there by taking images as a function of temperature. And in this case, I used the first image that we acquired at room temperature as a benchmark sample to then subtract it from additional samples so that we get rid of the structural defects within the iron rhodium thin film, because they won't be affected by the transition. So we've got iron rhodium thin film, iron MgO substrate. At 89 degrees, we can see the nucleation of a little small green domain on the side. And then as we keep on heating, we can see this domain grow along, outwards and inwards to the sample. As we keep on heating, it grows a little bit larger. We keep on heating, it becomes about halfway through the film. And then at 118 degrees, you can see sudden nucleation of a domain essentially facing in the opposite direction. And this nucleated and grew very, very sharpishly when we were doing the heating. And then if we keep on heating, we can see what actually forms is we've got this magnetization in one direction, magnetization in the other direction, and we can actually see that it's actually separated by a transverse domain wall between the two phases. Now, this is not something that you'd expect in the planar samples, but because this is essentially a cut up thin film, it's essentially formed into a needle, and this is something that you would definitely see in sort of one-dimensional samples. So it's not too unexpected in this case. Okay, so that was looking at cross-section. So now I'm going to move on to looking at planar samples. So in this case, we've got a planar iron rhodium thin film. This was on a wildfire chip. So everything in this field of view is a planar view of the iron rhodium. And there's slight variation in contrast due to the remainder of the substrate. And this is heated up to 200 degrees, so it should be in the fully ferromagnetic state. If we tilt it and saturate in one direction, and then tilt it and apply a small field in the opposite direction, we can actually nucleate domain walls at the side. And then as we apply higher fields using the objective lens, we can essentially nucleate walls at both sides, and then keep on applying higher fields using the objective lens. We can push these domain walls into a state where they're nice and parallel. And so the reason we want to do this is so we get a state of nice parallel domain walls, so then we can do quantitative measurements of the iron rhodium as a function of temperature. So in quantitative measurements, I mean of magnetic induction. So to do this, essentially we already know how thick the sample is from the cross sections. Just purely by DPC, we measure the deflection angle. We know what the probe size is from the aperture that we've used, and we know how big the detectors are. So we can use all these variables and take direct measurements of this value of deflection across the domain wall, which is in deflection angle here, normally in microradians. And then we can feed this back into this equation to try and calculate quantitative measurements of magnetic induction. So we've got the deflection angle, we've got a few constants, and the thickness. So we can chart this as a function of temperature. So in this case, we have the iron rhodium at 20 degrees, and we've got some very nice ferromagnetic domains, and we can measure from this little section here. As we increase temperature, what we can see is that these contrasts actually becomes slightly worse and worse, all the way up until we sort of approaching the Curie temperature at around 340 degrees. And we can actually see some disintegration or movement of the domain wall, which you'd expect as we approach the Curie temperature as well. So if we chart this as a function of temperature, what we see actually is that at room temperature, it's quite a strong ferromagnetic material, which does not agree with what we'd expect in the transition that I showed before. So we have a very strong ferromagnetic material. As we keep on heating, it becomes paramagnetic, approaching the Curie temperature. So one thing that we know from the sample preparation is actually that if we start off with this antiferromagnetic phase, and then during sample preparation, by back milling it, particularly with the hard MgO, and using the gallium FeRh, we can get ion implantation as well as potentially damage and destroy the stoichiometry of the iron rhodium and push it into this ferromagnetic regime purely by sample preparation. And something that we didn't do until much later is that we can actually recover the structure or the stoichiometry by annealing it after preparation. But in this case, we didn't do that, and that's why it's in the fully ferromagnetic state at room temperature. So if we move on to the separate sample, which is iron rhodium on nickel aluminium buffer layer on gallium arsenide substrate, in this case at 20 degrees, we can do the same methodology where we try and nucleate two domain walls and bring them together, which is what we did here. You can't really see it that well here due to both the gallium arsenide and nickel aluminium layers providing quite a mottled contrast due to the preparation. But there is a domain wall there, because as we heat it up to 80 degrees and then 140 degrees, we can actually see quite a nice contrast between the domains separated by the domain wall. If we keep heating up to 200 degrees and then 300 degrees and then 400 degrees, we can actually see how the contrast actually decreases again as we approach the Curie temperature. So if we go back to making quantitative measurements of saturation induction, we can see at room temperature, it's a sort of weak ferromagnetic. We heat up and it becomes quite a strong ferromagnetic material, and then it decreases as a function of temperature approaching the Curie temperature, as we'd expect. So there is a possibility that this small ferromagnetic signal is due to just maybe the surface of the sample being damaged by sample preparation, or a change in the slight change in the stoichiometry, but it matches quite well with the phase transition as we'd expect that I showed before, which was definitely a better result than the previous sample. Okay, so we've been looking at trying to get quantitative measurements from planar samples. And so one thing that we want to do, particularly with trying to create a device, is being able to control the position of the phase boundary between the antiferromagnetic and the ferromagnetic regime. And so to do this, we can actually include various dopants. So this is a sort of cross-section of the iron rhodium thin film. This is chemical analysis of it. So we have iron rhodium as we'd expect. But if you add a sort of dopant level or 1 or 2% of palladium, what you can do is you can actually bring the transition temperature down. So it becomes ferromagnetic at a lower temperature. But if you add iridium, you can actually bring the transition temperature up as well. So you can add these different dopants to try and change the transition temperature. And in this case, we wanted to see essentially if we can have within the cross section control the position of the transition, the position of the phase boundary between the phases, using a doping gradient. So we've got sort of at the top, we've got quite a high percentage of iridium, and this sort of gradually goes as we go through the thickness of the film. And because palladium brings down the transition and iridium brings up the transition temperature, you want to try and trap the phase boundary between the two phases at this sort of position here. So we can show that using these DPC images. So here we've got the thin film where we've got the protective platinum at the top. We've got the iron rhodium thin film in the middle and the MgO at the bottom. And we've got the doping gradient included in this. So at the top, we've got the iron rich side. And what you can see is that the color is significantly darker at the top than the bottom, and the green sort of signifies the ferromagnetic phase that it's in. So we've got a sort of phase boundary between the iridium rich side and the bottom side. As we keep on heating, we can actually see that this dark or antiferromagnetic phase becomes smaller as a function of temperature through heating all the way up to 200 degrees, where we can see it's become essentially fully ferromagnetic throughout the thickness of the film. And that's something that we wanted to do, to be able to essentially control the position of this phase boundary. And this will be the same on cooling, where again, we've got some hysteresis of heating versus cooling. So at 150 degrees, it's fully ferromagnetic. We cool it down to 90 degrees. You can see it starts to become antiferromagnetic at the top surface. It becomes more antiferromagnetic until down to 20 degrees, where we can see a nice phase boundary within this thin film. So this is a great result, but we wanted to keep pushing so that we have a doping gradient where at 20 degrees, it's absolutely fully antiferromagnetic, and then you heat it up to a reasonable temperature where we would have this phase boundary. So we wanted it to be fully antiferromagnetic at 20 degrees, not have this ferromagnetic regime as well. And that very much depends on the growth and the chemistry of the iron rhodium thin films. So still working towards trying to create a device, we essentially want to be able to control the position of the phase boundary, both by temperature, but also by applying current pulses to essentially try and change its state or change the position to change the resistivity of the thin film. And to do this, we use the lightning rod, because both we can apply heating, which essentially promotes the transition in iron rhodium, but then we can also apply current pulses through the sample to try and essentially use spin injection to move the phase boundary as well. So the samples were transferred onto the lightning chips across the biasing lines, and then we can apply current pulses using the dense holder. So this is a planar view of the iron rhodium. Essentially, at the top is a contact, at the bottom of the contact, this is a planar view of the iron rhodium, heated up to 150 degrees, so it's in a fully ferromagnetic state. And then what we do is we apply current pulses for 500 microseconds. And what that does is we actually see slight disintegration of some domains, and we can see movements of some domains as well. And if we keep on applying current pulses, we can see that essentially we're trying to move the domain walls into a fashion where they actually start becoming quite normal to the current pulse direction. So here we can see these domain walls or domains essentially becoming more perpendicular to the direction of the current pulses. And this continues up until a state where they become either annihilated when they're parallel to the current pulse direction, or in this case, this one's probably pinned. And we keep on applying current pulses to a state where they tend to be perpendicular to the current pulse direction. So it's worth mentioning that this is quite, in the grand scheme of this experiment, this was one of the large voltages that we applied. We applied voltage, we applied current pulses up to a point where nothing more would happen, and then we increased the voltage. And so again, we applied current pulses until nothing else would change, and then we increased the voltage again. So there is a possibility of dual heating, because we are increasing the current pulses. But that wouldn't necessarily explain why these domain walls become perpendicular to the current pulse direction. So there is probably an effect from dual heating as well, but we think that these current pulses are providing spin injection for them to become perpendicular to the direction of the current pulses. So this is just a summary of that sample. Obviously, you couldn't see all of the images at the same time, so I just wanted to point out that we've got these sort of domain walls here. Here we can see a little blue island, which then as we apply a high current pulse, and this is in current density, this little domain gets annihilated. We can see this domain wall gets moved quite significantly higher up, we get annihilation of quite the few lower domains up to a point where we've got these sort of perpendicular domain walls, or perpendicular to the direction of current pulses. So this was this initial state was how the sample looked at when we put it in under magnetic free conditions. And then once we apply these current pulses, it becomes into a state where they tend to lie perpendicular to the current pulse. So then to try and get rid of that, again, we saturate it in one direction. And as I showed with the quantitative measurements of saturation induction, we try and get these states where these magnetic domain walls are parallel by applying the objective lens and tilting the sample. And then we can apply, again, increasing levels of voltage or current density into the sample. We can see how these domain walls essentially become more perpendicular to the current pulse direction. And in this case, we can actually see that this domain becomes fully annihilated. We've got some remnants of this domain here. And then as we increase the current pulses, again, we can see that they become annihilated, where most of the domains essentially lie perpendicular, or the domain walls lie perpendicular to the current pulse direction. Which agrees essentially with what I was saying before. Well, hopefully it's not all Joule heating, and it is mainly due to the current pulse direction. So this is a sort of final example where, again, I tried to get parallel domain walls, and we apply increasing levels of current density, and we can see how we've annihilated or sort of broken up this domain wall here. We've got a thin needle to it. We increase the current density until essentially we get annihilate the original domain walls, and it looks like we've got some pin domains just at the bottom, which kind of look like horns as well. Okay, so we've been able to show that we can have imaging of the samples in cross-section, and then we can also show that we can image the samples with a doping gradient as well to try and control the position of the phase boundary. And then we can also show how we can inject current pulses to try and move the domain walls in a ferromagnetic state. So the final challenge essentially is what we want to do, and what I'm currently working on now, is get a iron rhodium thin film, which is doped between two contact layers of nickel aluminium. So essentially, so we can have conduction pathways for the current. So we can have the current in through one contact layer, down through the iron rhodium thin film, and then current out the other side. And what we want to do ideally is, if we have our doped iron rhodium in the middle, and therefore we have a gradient in transition temperature, so we can control the phase boundary essentially using temperature and trap it in this situation. If we apply a current in, hopefully we can use spin injection to essentially move the phase boundary down or up, and essentially by doing that we would be able to control the resistance of this thin film in a device, and essentially create a bit for a memristive device by controlling how much resistance is in this thin film. So that's the plan we're currently working on. It's challenging, but hopefully we'll get it done. Okay, so just to summarize, I hope you can see how beneficial using a series of Lorentz techniques like Fresnel, small angle electron scattering, DPC, and pixelated imaging can be used to visualize the dynamic evolution of the iron rhodium transition. Initially, we showed that there is a small signal at the interface between the iron rhodium and the MgO in cross-section. We can also show how this promotes the nucleation at the interface of the small ferromagnetic range of larger domains. And also in the planar sample, we can see how the transition proceeds by first nucleation of vortex structures, their agglomeration into larger domains, joining of little string domains, until we get long-range ordering of large domains throughout the transition. And we also managed to use quantitative DPC to show how there wasn't any transition on the iron rhodium on MgO, most likely due to damage during the sample preparation, but there was a clear transition in the iron rhodium, which was on the nickel aluminum buffer layer. Also showed how we can include doping gradients of iridium and palladium, which then can control the transition temperature, either by increasing it with iridium or bring it down using palladium. And then we can control this phase boundary position using both doping and temperature. And finally, to try and include current pulses as well, to use spin injection to try and move the phase boundary position, And by doing that, we should be able to change the resistance of the sample for a memoristic device. So with that, I'd just like to thank everybody who helped out with the experimental side at the University of Glasgow, as well as the funding, and thank you for your time. I think you're muted.
All right, Trevor. Yeah, I forget to unmute my microphone. So and thank you for sharing your research and for giving this presentation. We have one question from the audience at the moment. So another question also comes in. So the first question was from Bin Bin Wang, and she says, or he, "Hi Trevor, very nice work. I was wondering which package you are using to do the after process analysis, and what's the critical thin film thickness for such work in cross section?"
So packaging, do you mean for the processing of the 4D STEM data? We use a sort of in-house Python code, which was written by people within my group. I do believe it's online. So it uses Python. Well, I did use some C+ programming in a GPU before, because you get large data sets of about 8 GB for one image. So if you email me, I can send you a link. It's online, so if you're interested in that. For the segmented DPC, we use a code written within digital micrograph, where you take the signals from the 8 detectors, as well as the sum images and everything, and you can do quantitative processing within DM to get magnitude color images using that script as well. If you email me, I'm happy to send that if you use DM as well. In terms of critical thickness, we haven't really, well, we've had several samples, and the critical thickness, we're trying to focus on 50 nanometers. Oh, sorry, when you say critical thickness, do you mean in cross section the thickness of the sample or the thickness of the thin film? I guess that's worth knowing.
That's a good question. I cannot answer it because Bin Bin Wang has left. I think there was a mistake, maybe with the system or something, because first the question was posted, but it says, what's the critical thin film thickness for such work in cross section? That's the only thing I have.
Well, okay, so the thickness of the films is not something that I control. We're given what they want, and they do all the bulk measurements to begin with. So 50 nanometers was the main thickness. We did try and look at some thinner films without much success. In terms of the actual sample thickness, when you're looking within the TEM, the thicker it is, the bigger moment you're going to have, or deflection from the magnetic properties or the in-plane magnetization. So the thicker it is, the better it is for measuring magnetism. But obviously, the thicker it is, the worse it is for getting signal or electrons through it, depending on whether you're lying on a zone axis or not. So from the samples that I showed, I think the cross-sectional thickness was around 80 nanometers. If you go too thin, then you may sort of come across, through FeRh preparation of the cross-sectional samples, dead layers either side. So even though it may be, I don't know, 40 nanometers thick, there may be 10 nanometers either side that might not actually be magnetically responsive as well. So long answer short, in terms of film thickness, we look mainly at 50 nanometers, although we do have thicker ones. And in terms of sample thickness, around about 80 nanometers is best. Too thick, harder to get electrons through. Too thin, probably too much damage.
All right, I will be sure to notify Bin Bin this answer. It's recorded, so he or she can watch it tomorrow. Then the next question was from Andrew Stewart, and I'm just checking if Andrew Stewart if it's possible to ask the question live. Just see, but Andrew is at the moment self-muted. So I will just read out the question for him. So He says, wonderful work, Trevor. Is there a correlation between the gallium damage or defects in the sample and diamond wall pinning? If so, was this challenge in your analysis? Domain wall pinning.
There may be correlation for sure. We didn't necessarily, well, so the one sample with the nickel aluminium had a gallium arsenide substrate. So if there was gallium there, we would assume it's probably more from the substrate or residual from the substrate in planar view than from the actual gallium implantation itself. And we didn't really look at the chemical analysis. It was a case of just trying to get something that works magnetically. But so in some examples, the domain walls do tend to pin in the same area. And there is most likely a defect causing that, but I'm not sure whether that's gallium implantation necessarily. I don't know, yes or no, basically whether it's gallium causing the pinning or not. In the planar samples, we didn't really see too many pinning in the cross-sectional samples. Certainly, we can apply fields, and we did apply fields in the cross-sectional samples to move the domain walls anyway. So we can unpin them using the objective lens and tilting it. But no, it's a great question. I can't 100% say it was from gallium.
All right, Andrew, I hope that answers your question. Thanks, Andrew. Thanks you for your answer. So another question was from Tanya, and the question is, let's see, thank you for the great presentation. Can you apply beam mask for additional analysis going backwards when you did not utilize beam masking?
No. Well, so if my understanding is correctly, you're talking about the pixelated stem where you apply a mask to the central probe. That is done on data that you start off with the central probe and then you apply the mask afterwards. So the original results that I showed is using the segmented detector, where we don't have images of the probe at every scan point. So you can't retrospectively go back to segmented DPC and apply a mask, because you're essentially using intensities across the segments of the detector rather than looking at the image of the beam at every scan point. I hope that.
All right, Tanya. Yep. I see. Thanks, says Tanya. Another question from Panagiotis, and the question is, first of all, thanks for the nice presentation again. And is it possible to perform atomic resolution imaging of the magnetic properties of atoms? Namely, I ask it if it is feasible with the new IDPC technique.
I would say you'd have to have a very good microscope. So IDPC, from my experience, depends whether you have the objective lens on or off. So if you turn the objective lens off, then you reduce the resolution, you won't see atoms. Another issue, I would say, if you're trying to look at individual atoms, it would have to be samples that are individually, well, one atom thick, like graphene. If it's one atom thick, then regardless of how strong the magnetic moment around the atom is, it's probably not going to be large enough to deflect the electron beam. So not particularly with these samples, like I said, there's 80 nanometers thick. There's lots of atoms in the pathway for the electron beam to be deflected by the net magnetism in a certain direction. To look at magnetism of individual atoms, I mean, you can get the resolution. I know Shibata in Japan can get atomic resolution under magnetic free conditions. Getting the resolution is one thing, but actually getting direct measurements of magnetism at that resolution, I would say, is much more challenging. So If you want to look at individual atoms, you'd have to look at 1 nanometer or 1 atom thick samples. I would say it's very, very difficult to actually get direct measurement at the moment because you're not having enough material to transmit through to actually get a deflection of the beam. You can image, but measuring magnetism is slightly different.
All right. I hope that answers the question, and thank you everybody for asking many questions. I hope to see you at the next webinar, and of course, I want to thank you, Trevor, for today. This morning we had your first presentation, and now the second. So thank you very much for taking the time to share your knowledge and your experience.
You're very welcome. It was a pleasure. Thank you.
All right, great. Okay, everybody, have a great day, and see you at the next webinar. Thank you for joining.
And that brings us to the end of this Nanotalk. To stay informed about upcoming webinars, I invite you to follow our social media channels, LinkedIn and Twitter. I also invite you to sign up for our monthly newsletter, in which we share interesting in-situ research and technological innovations. I want to thank you for watching and hope to meet you at one of our next webinars.